Well, hello all, and welcome to our first HDTN Community Day. I'm Daniel Rabel of the NASA Glenn Research Center here in partial representation of our team. I wanted to just give a few introductory notes here. So we are going to be recording today's presentation, and what we're going to do is then host that on our website for those that aren't able to make it here live today for future viewing, or if you want to go back and view things later when you're working with HDTN. And we've split it up into two sections. So there'll be a presentation portion, which we'll start with, and then there's going to be a Q&A portion at the end. What we'll likely do with the Q&A is transcribe that. I think it'll be easier for information dissemination. And so we'll create like an FAQ document from the Q&A section. So what I encourage you to do is formulate your questions during our presentation. And if you want to pop them in the chat, I can put all those together and we'll start going down the list. Or also, if you just want to come off and mute during the Q&A and do things verbally, that's fine too. We'll handle them. That's what we're here for. I certainly would like to thank the NASA Space Communications and Navigation Program for supporting this work over the years. And I absolutely wanted to thank all of you for not only participating today and showing your interest in HDTN, but in giving us feedback along the way and in the future for helping us to refine our product in order to be a better result in the end. So the way today is going to flow, we're going to lead it off here with one of our developers on the team, Brian Tomko, who's going to walk you through the architectural description of HDTN. And then from there, Blake LaFuente is going to show you how to access the files and compile them to run an instantiation of HDTN in a TCP loopback test, as well as use some of the services that we've built into the product. And then lastly, in the presentation portion, Nadia Cortas is going to then show you how to set up multiple nodes in a test and also use LTP, the Liquid Lighter Transport Protocol, as well as run the simulator product in that and perform a demonstration for that. And then we'll open things up for the Q&A. And so taking it from the top, HDTN is our implementation of the DTN standard. And what we've done is we've targeted higher rate RF and optical link applications. When we say higher rate, we're typically looking at things that are gigabit per second or above, although we wouldn't necessarily limit it to that. But that was our goal in putting together this implementation. We've spent the better part of this past year doing a lot of testing on HDTN, particularly with interoperability with other implementations, such as the Interplanetary Overlay Network ION and DTN ME, Marshall Enterprise, both within our test bed at Glenn and over at the Johnson Space Center as well. We're doing all of that to get ready for several really exciting space technology demonstrations, such as going up on the International Space Station and supporting the laser communications relay demonstration. If you're not as familiar with HDTN, that's fine. We've put together a website that we're going to continue to maintain over time. So we've got some good descriptions of what HDTN is there, a few videos for you to watch. All of our publications that we release are accessible through that website without any paywalls or anything like that. And this is also where you can get the direct link to our GitHub, which Blake will steer you through and how to use to access the latest revisions of our released code, and also where this video will reside here in the near future. So again, I thank you in advance here for your participation here today. Really looking forward to sharing with you our product, what's under the hood in that. And with that, I will pass it over to Brian Tomko, which will get us into the architecture portion. So thanks again.
All right. So jumping right in. So here you see the HDTN architecture highlighted in gray. And there are 5 main components to HDTN. We have the ingress, the egress, the storage, the scheduler, and the router. Now, these components communicate with one another over 0MQ sockets, as you can see there with the black arrows. Because of 0MQ, HDTN has the ability to run in a distributed architecture if a user so desires. So in other words, so the ingress component can run on its own process on its own computer, and egress and storage can run in their own processes on other computers, however the user so desires. And when running HDTN distributed, all 0MQ sockets would communicate over TCP. However, in most cases, we recommend running HDTN as a single process, which is an executable called HDTN-1-process, or HDTN1 process. When running HDTN as a single process, the ingress, egress, and storage components run within their own set of threads, and the 0MQ sockets no longer communicate over TCP, but rather as what's called a 0MQ exclusive pair, which requires zero memory copying, so it's really fast. However, as of today, the scheduler and router components of HDTN must be run in their own processes, but that should change very soon. The ingress component, you see there, receives bundles from the various convergence layer adapters available to HDTN. The egress component sends bundles out using the convergence layer adapters as well. Now, the storage component stores bundles using a striping mechanism across one or more solid-state drives whenever the link for the next hop for a bundle is unavailable. We have the scheduler, which sends link up or link down events to ingress and storage to determine if a given bundle should be forwarded immediately to egress or sent to storage. And then we have the router module. The router module gets the next hop and the best route leading to the final destination using one of the algorithms in the routing library. Currently, we support the contact graph routing, or CGR, which uses Dijkstra's algorithm, and that's the default algorithm used in HDTN. However, there is also a new routing algorithm called contact multigraph routing in the library, which can be used as well, which can be a much faster implementation of CGR. The router then sends route update events to egress to update its outduct and to the outduct of the next hop. If the link goes down unexpectedly, or the contact plan gets updated, the router gets notified, recalculates next hops, and then sends these route update events to the egress. If you can go to our next slide, please, Blake. Right. So I'll talk a little about our GitHub HDTN directory structure. So at the top there, in our source directory structure, one of the folders there is called Common. Now, Common contains many of our common libraries and utilities used all throughout HDTN. Everything from version 6 and version 7 bundle codecs to all the convergence layers used across HDTN, to applications such as BPGen and BPSync, and to also just basic utility functions. Now, the next folder there is called Module. The module directory contains all of the components of HDTN, but it also contains a web GUI interface to HDTN, which can be optionally compiled in, as well as a folder there called UDP delay sim, which is what we call a UDP proxy process, giving you the ability to place long delays on UDP packets, which is definitely useful for simulating long delays with LTP. And it achieves this through allocating large buffers to store UDP packets and delaying them however long you specify. Now the config files directory there contains test configuration files in the JSON format for HDTN, as well as other JSON config files for BPGen and BPSync. And in this config files directory is a lot of loopback demos that you can base any of your configurations on as a starting point. Now the test folder there contains example test scripts for both Linux and Windows, which use the config files from the config files directory there. Now, all of HDTN's directories of modules and libraries, I want to talk a little bit about our CMake. There's I know that how we do the CMake has been of interest to many. So talk a little bit about the CMake. So all of our HDTN directories of modules and libraries contain their own CMake list.txt file. Now there's a root CMake list.txt, and that adds all those modules or libraries to the overall HDTN project using the CMake add subdirectory command. Now, it should be noted that the HDTN CMake files are written using modern CMake paradigms. One example is called dependencies as targets. And what doing that does is it makes it much easier and cleaner to manage a multi-platform library like HDTN. Now in addition, our CMake does it does package config information. So package config information gets exported to the installation. You know, whenever a user wants to do a make install from the generated make file that CMake produces. Now, there's an example in our test folder. In our test folder, we have our unit tests, but also in there is another project in addition to our regular unit tests called unit tests import installation, and it's got a CMake lists.txt file in there, and it's basically a copy of our regular unit test, but it's different in this way, in that unit test import installation uses the find package CMake function, so it can import package config information from a installed installation of HDTN. And what that imports is everything about how you compiled HDTN and makes it available to your project. Well, why would you want to use this whole package config thing? Well, it's nice that the package config information is great for users that may want to write custom software projects that use only portions of the HDTN code base. Perhaps they want to use one particular convergence layer, but they're not interested in the rest of the code. They could do a make install of HDTN and then simply use the package config to import specific libraries of HDTN that they may want to use for their own individual product or project. Now, the other thing I wanted to note about the HDTN CMake is that it tries to optimize the build as much as possible. So it will test the compiler to see if it supports more recent C++ standards. Rather than using C++ 11, which is the default, it will try to detect if C++ 17 is supported by the compiler, so that anywhere that there's some optimizations throughout our code that can take advantage of little optimizations that are only available in C++ 17, the CMake will detect that. The CMake will also test the compiler and the actual processor for specific x86 hardware instructions, and it will utilize those if available. You know, one of these the common ones is the Intel CRC32C compiler intrinsic, which is very nice for bundle protocol version 7, or if you're using CRC32 to verify your blocks, it makes it much faster in processing that. But there's many places where we use optional hardware acceleration throughout our code, especially in SDNV and CBOR encoding and decoding. And I want to say finally, our CMake supports building its libraries as either static or shared, using CMake's generate export header, which is required for building or using DLL files on Windows, and it's also for using GCC's new C++ visibility support. And then last thing I want to mention, a little side note, one of the folders not mentioned here in this structure that's very recent is a folder in the root directory called Building on Windows. And so if you want to run HDTN natively on Windows, all you need is to make sure you have a version of Visual Studio installed, either 2017, 2019, or 2022, as well as an installation of 7-zip and Perl. And all you got to do is run the PowerShell script inside that folder. And what that will do is it will pull the latest HDTN from our GitHub repository, and it will also pull all of the dependencies that HDTN uses and build them from source as shared DLL libraries using your most recent installed version of Visual Studio. And you can look at our README or user guide for more info if you want, if you're interested in that. Then if you can go to my last slide, please, Blake. Right, so just an overview on some of the applications that we provide with HDTN. So we have BPGen and BPSync. BPGen is a tool that generates bundles of any specified size. It's intended to be used with its receiving tool called BPSync. Now, it's not a component of HDTN, but it does share the same code base and libraries as HDTN. So basically what that means is it can use any of the convergence layers available to HDTN. So it's sort of like a lightweight, these applications are sort of like lightweight HDTN without storage capability. Now BPGen and BPSync, their config files share a subset of the HDTN config files, so that it will look very similar. Then the other thing I want to note is that the BPGen and BPSync source code, those utilities are for the source code is very small, because BPGen derives from a helper C++ class called BPSourcePattern, and basically just overrides two virtual methods. BPSync derives from a class called BPSyncPattern and overrides one virtual method. So what that means is any user who wishes to write their own utilities that generate and or receive bundles using any of our convergence layers can simply inherit from these helper classes and just simply write a few lines of code, and you can have your own bundling utility for your custom application. A couple other utilities we provide are BP send file and BP receive file, which also inherit from these helper classes. The BP send file is a tool that sends either a single file, or it can send a directory of files with recursion, and it takes those files and breaks those into a max specified bundle size. And it's intended to be used with the receiving tool BP receive file. BP send file can remain open after it's sent all of its files, and what it can do is it can monitor the directories up to a user specified max recursion depth. It'll monitor those folders for any newly added files, and it can just send it. So you can just basically leave BP send file open and drag and drop files into the folder, and it will send them off. The BP receive file tool receives the bundles sent from BP send file in any order, and it reassembles these file fragments and then closes the file when all file fragments have been received, and it writes them to a user specified directory. And the last little application on here is called bping, and that's a tool that's also derived from BP source pattern, and that generates ping bundles, and it's intended to be used with any bundling agent that supports an echo service. HDTN has an echo service built in with a service number specified as its config file, in its config file under the JSON variable called my BP echo service ID. And also all the HDTN applications such as BP sync and BP receive file that inherit from the BP sync pattern have a echo service number currently built in of 2047. So you can ping the applications if you want, and as long as those applications are set up to be bidirectional. And with that, that is all I have for my portion.
All right, so next I'm going to walk through how to build and run HDTN. The demo I'm going to show will be HDTN running in a loopback test using TCP convergence layer. And so what's going to happen is BPGen will generate bundle data, which will send to HDTN with ingress, egress, and storage running as a singular process, and then forwarding those bundles along to the BP sync application. So let me bring up a virtual machine containing this. One moment. All right, so the first thing you will do is go to the public GitHub repository. You can just find this by Google searching NASA GitHub HDTN. And you can go here and copy the address to clone it. Now for this demonstration, I'm going to be building this on Linux, but as Brian said, this can also be built and run on Windows using Virtual Studio. And the instructions to do that are also in our user guide and README. All right, so I will just clone it here in my home directory. Okay, so I'm going to go into it and create a build directory. And then the next necessary step is to export HDTN source root, which is needed to run HDTN. And I'm just going to set that to my working directory. All right, so the next steps are only necessary if you are building the web user interface with it. For that, I'm going to download and compile an application called Civet Web, which enables us to easily host a web server as a lightweight application. So first I need to make the directories to do so. So I'm going to make an external directory, and then external include, and then external lib. And next, I'm going to download Civet Web from SourceForge. So again, all I have to do to find that is just Google SourceForge and Civet Web. But the links to both, well, links to this will also be on our GitHub and user guide. But you should go down here. And since it's Linux, I'm going to download the tar file. So I will get out of here and go to my downloads directory. And I will unpack the tar file. Go into it. And next, so to compile, to build it, the instructions are available on Civet Web's GitHub page as well, and as well as our user guide. But just to show this, make build. And then make clean with WebSocket equals 1 and with CPP equals 1. All right, so now I need to port over the header files and the library file. Okay.
Blake, was it supposed to be make clean lib?
Oh, it was not make clean. I apologize. Thank you. It was just make with. Oh no, it was make clean lib. It is make clean lib. I forgot a word. Thank you, Brian. Yeah, and so there's the library file did compile, so that's good. All right, so we can copy that over. And then we're going to copy over the header files. All right, and that's all we need from Civet Web. Let's clear this up. Clear. All right, so going back into our build directory, we're going to run cmake ... And then because we are building it with the web interface, we actually need to go back into the CMake cache and set that to on. It's off by default. And so you go down, scroll down all the way to the bottom. So I think something went wrong here. Okay, yes, it is right. Okay, so make sure. Is use web interface equals true. I may have passed it.
Blake, that all looks correct. I think you just go to the very top of the CMake cache.txt and then do a search for the use web interface. That would just page up to the very top.
Oh, okay, here it is. Okay, thank you. I thought it was off here. Thank you, Brian. Ooh. I can't seem to scroll down to it. All right. So scroll down to use web interface so you can find where I did with it. Oh, I did pass it way in the beginning. Thank you. Okay, so it did compile correctly. Yes, I just had to go here and it scrolled too far past it. All right, and set you have use web interface to on. All right, and so now you need to run cmake ... again. And then you can run make. And now normally when we build this, when we build HDTN, we use -J8 to compile using 8 cores, and so that way it speeds up the compile time to do so. Even so, it takes a few minutes, so I'm just going to actually just switch over to a different VM with the exact same bill of environment and settings and everything using the exact same instructions I just did. It's just already built in advance. Okay, so again, home directory, HDTN, ls. And so the loopback test is actually already in the home directory. It's just called run script. And so I'll go into it to show you what it contains. And so it runs 4 different modules. It runs, like I mentioned before, bpgen to create the bundle data, the scheduler to determine the routes, a HDTN one process, so it's running ingress, egress, and storage, and BP sync to receive the files. Now you can see here that we're running them, starting them in backwards order. And this is because if we create files and then send them forward and the destination isn't on yet, that will cause errors. And so we start them in backwards order, and then we close those processes in the order of sending the file. So close bpgen first and BP sync last. At the top here, you can see we have config files. The ones for sync and gen as outside applications are pretty simple, but I'll pull up the one here for this test, which is this tcpcl JSON, just so you can see how it's configured. Okay, as you can see, there are many fields to be aware of. We go through each and every one of these on our user guide, but for the most part, we only adjust a few of these. Within the indux and outdux vector, you'll see that it is set to a specific convergence layer. Some of the fields do change by convergence layer. So if you go through our GitHub, you'll find examples of each convergence layer we currently support. But for in this instance, it is TCP. It's convergence layer. As you can tell here, the indux and outdux are vectors. And so HDTN can support multiple indux and outdux as it runs. Some fields you should be aware for this test, because it is a loopback test. The destination, which it says the remote host name, is localhost with the port being 4558. You need to make sure to check the final destination EID URIs are correct. Down here we have we set our storage capacity, which is 82 gigabytes striped across 2 files. And TLS is another security measure that can be added as well, which may be useful in different use cases. Okay, and now I'll go and run it. So as you can see, as it starts up, it'll tell you log information with what module that information is coming from is read through it. It sets the web server at localhost 8086. So I'll go there. And here it is under web GUI HTML. Now at the top here, you can see the current data rate coming into the ingress module. Don't let these data rates kind of confuse that. It's a problem with the speeds at the moment. It's just because I'm running in a compressed VM. But it'll tell you the current data rate, the average data rate, and the maximum data rate over the course of its running. On the next row, we have graphs. And so the first one will give us the data rate of ingress module, the one for the egress module. And this one tells you locations of the current bundles. And so if there is some sort of delay or disruption that prevents a file bundles from going out immediately from egress, it'll put them in storage, and it'll let you know what percentage of your bundles are in storage currently versus those that were sent to egress. Again, because it's a quick loopback test, storage wasn't really used. Down below that, I'll tell you the bundle count that was sent from egress, the ones that were sent to storage, the number of bundles sent overall, and the amount of data sent. And we have pretty much the same thing on the other for egress other than storage. By the end of the year, we hope to display more information here from the storage module specifically, and then we're going to implement specific data points for the different convergence layers, and I believe LTP will be done first. And so with that, I think I'll turn over to Nadia, who's going to go over a multi-node test.
Yeah, thank you. Hi, everyone. So do you see my screen?
Yes, we do.
Okay, great. Okay, so in this test, we are sending bundles between two machines running HDTN using Licklider Transmission Protocol LTP convergence layer. So the sender, node 1, will run BPGen, scheduler, and HDTN1 process, and the receiver, node 2, will run BPSync, scheduler, and HDTN1 process. The run scripts for these tests are located under, I put the links here, LTP 2 nodes test in the public GitHub. So let's have a look at these scripts. Okay, so yeah, so this is for, first of all, we have this, the main script. So this is for node 1. We're using BPGen to send bundles. For node 2, it will be BPSync. The main thing is, we're setting bundle rate to 0 to send bundles as fast as possible. And we're using a contact plan when it is always up. The contact plan, I think, yeah. So let me find. So the contact plan is located under model scheduler. So this is where currently we're keeping all our contact plans. And for this test, so we have all the contacts, all the nodes on the network. So, and then we specify the end start time. If you want to send, make sure the link is available all the time. We make sure we specify a high end time, in this case, 2000 seconds. So, and then we specify each contact has a source destination, and then we have a final destination. In this case, we're sending to the node 2 is the final destination.
Nadia, can I ask
yes.
a question, if possible?
Sure.
This is Apurva Modi from Aeronaculus. So
yeah.
Will this contact plan change as the orbital relays move around the moon? Or right now there's no provision for that? This is just a static file.
Yeah, currently it is just a static file, and we'll be using actually the web interface to modify that. But there is on the cognitive, Rachel can provide more information on that. We already have a way to reload the contact plan if needed, and that will update the whole system. So the routing will change, and yeah, so link. So basically the contact plan can be updated dynamically.
Okay, and so this will be interfaced to say some SDK or something like that? That's where the contact plan will come from?
Currently, you mean how do we generate the contact plan?
Yeah, correct.
Yeah, we using so like we are so right now it's not in this code. We're just using another tool to generate contact plans. So we also so Bob Shorts can provide more detail on that, and we even simulate for real Starlink, so big contact plans up to 1,000 nodes. But for the sake of these tests, we're keeping small contact plans.
Okay, thank you so much.
Sure, you're welcome. Okay, so so in this case, I was mentioning we specify, so each contact has a source destination. In this case, like it's the next hop, and then the final destination. And let's go look at the config files. So on the sending side, we were having an HDTN, the HDTN and BPGen config files, as we saw here on the run script. So we have HDTN, BPGen, and then on the receiving side, we were having BPSync instead of BPGen config file. So, but we're looking now at the main ones that need to be changed are the HDTN config files. So we need to make sure, so basically on the sending side, we have VPGen has an outDACT over localhost to the HDTN. In this example, VPGen has an outDACT over localhost to the HDTN, and BPSync has a localhost inDACT, both of which are over LTP convergence layers. So these are specified. So we have like, we need to specify the inDACTs in our inDACT vector and then the outDACTs. With the correct port numbers and final destination nodes. So in this case, our final destination is IPN21. And then we need to update the remote host name with the correct IP address. So this is the IP address of the host, like the destination. And then we need to update the main LTP parameters, such as the remote LTP engine ID and this LTP engine ID. So this LTP engine ID will be the same as our node ID here, my node ID. And we also need to update some other LTP parameters, which are detailed as needed. It's detailed more in the user guide. But mainly for this test, we updated the LTP data segment MTU to make sure UDP packets stayed under the Ethernet maximum transmission unit of 1500 bytes to prevent fragmentation. LTP max expected simultaneous sessions. This is the number of expected LTP sessions for this engine. And then for the storage, we allocated 82 gigs striped across 2 different files. Okay, so this is mainly for this test. And then now we're gonna show the demo. So the terminal on the left is for node 1, the sender, and on the right is for the receiver. On each of these machines, we have already installed HDTN. We need to set HDTN source root correctly, so it's the main root, and then run the run scripts, which are already in the public GitHub. Both these nodes will have also the same contact plan. Okay, so here you see BPSync, all the processes. So on the receiving side, we have BPSync, HDTN, egress, ingress storage. On the sending side, we have main HDTN processes and BPGen. So the scheduler, you can see here, sending link up events for all the links, since we configured it to make sure link is always up. And then we see that we are receiving our bundles on the receiving side, and this is the data rate. So 631 megabits per second here, around that, yeah. Okay, so next. Okay, so next test relies on having, it's a 4 nodes test, and it relies on having 4 machines running HDTN and is using the router model. So node 1 in this case, will run the router, BPGen, the scheduler, and HDTN1 process. Node 2 and 3 will run the router, scheduler, and HDTN1 process. And the final destination will run the router, scheduler, HDTN1 process, and BP sync. And I put here the links which are in public GitHub for this test, for the run scripts and the config files. So in this test, the HDTN config outdact vector next hop is configured to node 3 originally, but after the router computes the optimal route to the final destination, the outdact will select node 2 as next hop instead. So let's have a look at the config. So here we have at initialization, the HDTN JSON config file. This is the config for node 1. For each of these nodes has all possible next hops. So we have next hop here. Possible next hop is 3 and then 2. So if we have multiple hops leading to the same final destination, only one outdact should be initialized with the final destination vector, and the other next hops outdact should be dormant. So having no values initialized in their final destination JSON fields, like in this example. Next hop can be either 2 or 3, but after the router computes the best route, it will send an event to egress, which will update the outdact to node 2, so that next hop is node 2 in this case. Okay, so next we have the HDTN simulator. The setting up test for HDTN for a large number of nodes was time consuming and didn't scale. So we developed an HDTN simulation tool that would replicate the routing decisions HDTN would take, but in an accelerated simulation environment by adding a routing module to DTN simulator. And this was built on Omnet++ framework, which also provides metrics collection, network flow diagram generations. Here you can see the simulation with 28 nodes, showing the different, so. Okay. So next we have the HDTN simulator configuration and installation steps. Currently, simulating HDTN with DTN sim can only be done on Linux. We tested it on both Debian and Ubuntu, and the steps are as follows. So we need to first install HDTN, download and install Omnet++ version 5.7, install DTN sim. We have all the details in our user guide as well. And then configure Omnet++ for simulating HDTN. So here we have an HDTN demo simulation that you can use as an example. So you can edit this. So in this directory, HDTN demo, we have this HDTN demo.ini file. So you can edit that file and update the DTN sim. After doing the previous steps, you just edit this file, update DTN sim central HDTN source root, this one, with the absolute path to your copy of the HDTN source code in HDTN source root, and then you should be able to run the routing test simulation. There are the main HDTN parameters, like HDTN specific and INI file parameters are, so here we have first the contact plans. So for example, for this test, 28 nodes that I showed earlier, we have the contact plans both in ION format for DTN SIM and JSON format for HDTN. And a contact plan in ION format should be kept in a location reachable from the directory your simulation INA file is located in. And then for each contact plan in ION format, there must be a corresponding equivalent contact plan in JSON format stored in under HDTN source root model scheduler source. And then the other parameters are the DTN routing, this one, and then HDTN routing mode, HDTN source root. Yeah, so yeah, that's mainly it for the for this part. More details can be found under the simulation section in our user guide. And we also have a Ubuntu VM that's available for download with HDTN, Omnet++, and DTN SIM installed and pre-configured for HDTN simulation. So here's the link for that on the user guide. And thank you for your attention. And yeah, that's all I had.
Wonderful. Thank you, Nadia.
Sure.
And so as you see on Nadia's screen right now, she's sharing the user guide. We'll be sharing that out to all of you likely later today, just in case there was any, we learned something that maybe we had overseen. Gives us an opportunity to add some stuff at the last moment, but we want to make sure you get the latest, greatest, and so that will do. Again, thank you so much for everyone for joining us here. I hope you found this very beneficial. I know we did. And like I said, we'll be sharing the user guide with you a bit later and updating our website. We'll be hosting this video up there as well, and likely creating some more content, maybe even in video fashion, a little shorter than this, but maybe some, we were thinking about maybe doing some quick bootstrap videos for those that just need just a quick, I got to get it running right now, and I've got 2 minutes. We might be putting some stuff like that together as well. So thanks again. Really appreciate it. Be well and enjoy your weekends. And thank you again for all the kind words. Much appreciated. Thank you to the team too.